Okay, we're going to continue on here. We got into the next chapter, which is equilibrium. And as we talked about, equilibrium is basically a certain type of reaction like this. And it is a reversible reaction. And basically, there is, again, a forward direction, which goes from the reactants to the products. There's also a reverse direction, where at some point when you build up enough products, they will come back together and make your reactants and kind of head in the reverse direction. It will eventually reach chemical equilibrium. And as we talked about, when we reach chemical equilibrium, what we're really referring to is the rate of the forward direction there will equal the rate of the reverse direction. And again, it doesn't mean necessarily that you have the same amount of stuff on each side. It means pretty much just as quick as you kind of go to the right there, you're going to come right back to the left. And what that ultimately will do is, as we were talking about, sort of lock everybody into where they're at that point in terms of their concentration. Their concentrations will remain relatively constant all through that process. And also, if you happen to be dealing with pressures, because their concentrations remain pretty much constant, so will the pressures if you're dealing with sort of a gas mixture or reaction that's basically occurring in that case. We have an expression that if you have a reaction like this, which is known as the equilibrium constant, and that is our capital K, and that basically is our products, concentration of our products divided by the concentration of our reactants. And when we do calculate K here, which again is capital K, we do take our products. And in this case, unlike what we do in sort of rate laws, we do use the coefficients as the exponents when we do this. So the concentration of C to the C, concentration of D to the D, and A to the A, and B here to the B. So we do take the coefficients from the balanced equation. They do become the exponents there when we do this. Now, K is one of the few things sort of in chemistry that actually usually does not have units associated with it. So it is just a number. And we could use that number, as we talked about, to help us know sort of what we should expect, for example, when we do reach equilibrium. So if we have a K value that is large, what that means is when we reach sort of equilibrium, we would expect more products perhaps to be there. And that's just mathematically speaking, if you have a larger number up on top divided by a smaller number, that's going to give you a larger number. So again, you should have more products than reactants. If you have a small value of K, that means when you reach equilibrium, you should have mainly reactants. Same sort of math idea. If you have a smaller number on top divided by a larger number on the bottom, it will give you a smaller number for K, and that's what we would expect. Once again, when we're sort of thinking, is this sort of considered a large or small value of K? Pretty much anything 1 and above is considered large. Yeah. So anything basically a K value of 1 or above is considered large. Anything less than that is considered a small value of K. And there is definitely extremes on that. So as I might have mentioned last time, you can have a K value that's like times 10 to the 34, which is an extremely large number, way larger than 1. Or you could have like a K value that's extremely, extremely small, like times 10 to the minus 54, which is a super small K value. And you really can have a K value anywhere in between that. So there is sort of different levels of small, large, in terms of K values. And, you know, if you have something that's really, really a large value of K, even though it is still a reversible reaction, it mainly is kind of almost like a one-way street heading to the product side. And if you have a really, really small value of K, it also is really going to kind of hang out on the reactive side. It's not going to really go in the forward direction in that case. Now, when we look at K, as I mentioned, we could use it to determine reactants or products. It is a constant value as long as the temperature stays the same. So the temperature is the only thing that could actually affect the value of K. So I think we might have talked about it last time as well. You know, if you ran several experiments, for example, at 25 degrees Celsius, and one of the things that sometimes people have a hard understanding or misunderstanding of is it doesn't really matter in the sense of what you start with in each of those sort of experiments. You could start with all reactants, you could start with all products, you could start with a little bit of reactants and products when you're kind of throwing everything into the beaker. It will always come, as long as the temperature remains the same, to the same ratio of products to reactants and give you that same number. I think maybe I did an example of getting a K value of 2, right? And we could do, like, obviously 4 divided by 2 is 2, 2 divided by 1 is 2, 8 divided by 4 is 2. So those are all different sort of numbers, if you will, but the ratio ends up being the same no matter what it happens there. So again, you could do like 5 different experiments at 25 degrees Celsius. When you go to calculate that K, regardless of what you started with in each of those, it should come to the same ratio when it's all said and done. Now, as I also mentioned, if you then, for example, raise the temperature to 50 degrees Celsius, you would then have a different K value at 50 degrees Celsius in comparison to 25 degrees Celsius. But again, if you ran 5 experiments at 50 degrees Celsius and you calculated the K value for all those guys at 50 degrees, they all should be the same at 50 degrees. But when you compare 50 to 25 degrees Celsius, those K values will be different. Any questions on any of that there? All right. So here's, as we look at it here again, we have Mickey here plus this, and upside down Mickey has a K value there of 25 degrees Celsius. This would be, would we expect mainly reactants or products in this reaction when we reach it? Yeah, we would. Again, this is considered a large value of K, which means, technically speaking, the forward direction should predominate because we should end up with more products, say, than reactants in this case. Now, when we look at equilibrium, as I mentioned before, you can definitely write an equilibrium expression for reaction. And in a homogeneous equilibrium, homogeneous is like a homogeneous mixture. Everything looks the same. So when we talk about a homogeneous equilibrium, everybody's in the same phase. So in this case, everybody here is in the gas phase. And we can write our equilibrium expression here, which is the concentration of NO2. And again, we square it because of the coefficient, divided by the concentration of N2O4. The coefficient here is 1. Obviously, we don't usually put 1s in there for chemistry. And that is the concentration. And again, a reminder, bless you, that the brackets here does mean concentration. And typically what we're talking about, again, is molarity, which is our moles per liter, is typically what we're doing here. This equilibrium constant, because it is dealing with concentrations, is sometimes referred to as the Kc value, C meaning that you're calculating it based on concentrations. Now, in this particular reaction, we have all gases happening here. And when we think about gases, we oftentimes think about pressures associated with gases. So we could actually write an equilibrium constant that deals with pressures, you know, like we get something like our PV equals nRT, right? Our ideal gas law here, once again, as we talked about, should be atmospheres, liters, moles, 0.08206, and our temperature there should be in Kelvin. So we could also write, in this case, because they're all gases, we could write what is referred to as the Kp expression, P meaning pressure, and it works the same way. We would take the partial pressure of our products here. We still need to square it because of the coefficient, divided by the partial pressure of N2O4. And we could have a Kp value, our expression, for a reaction that involves gases. Now, the Kc value and the Kp value usually are not the same actual numerical values, or they're not usually the same actual number. They actually can be, but usually they're not. But they will tell you sort of what is going on. in terms of that reaction, they'll give you the same information. So if you typically have a large value for Kc, you also will have a large value for Kp, a small value for Kc, a small value for Kp as well. So they do sort of agree in that sense. And again, in most cases, they will not be really the same value. When we're dealing with pressures and equilibrium, it is atmospheres typically we want to use as the units. That's usually the standard unit. A reminder, right? In 1 atmosphere, there is 760 torr, right? And 760 millimeters of mercury. Later on, we'll do some calculations in this chapter, which are important calculations. And if you come across a calculation like we will see later on, and it is dealing with pressures, you do usually need to make sure that they are in atmospheres and convert them. Even if they give you your pressures, for example, in millimeters of mercury, and they want the answer sort of in millimeters of mercury to do sort of the equilibrium calculation that we'll talk about a little bit later on, they do need to be put into atmospheres, do the calculation, and then kind of convert out at the end of it. So it's very important to kind of keep that in mind as we go through it. Now, we'll kind of jump a little ahead of here, but when we write these equilibrium expressions, we basically include everything in there except a couple of things are not included. So when we write the K, what is included is anything that is a gas and anything that is aqueous or water environment. What is not included, as we'll talk about in kind of C, is anything that is a solid or a pure liquid. So things that are solid and pure liquid do not really affect the equilibrium for a couple of reasons. Solid things are just kind of sitting there, so they're not really participating or doing much along the way. And liquids like water, for example, their concentration is so high it doesn't really change throughout sort of the process as well. So liquids and solids are not included when you write the equilibrium expression. It is only really things that are gases, which if you think about are flying around pretty active, right? And moving around, have a lot of energy usually. And aqueous things. And aqueous things is where we find ions, for example, right? Floating around in solution. So they're floating around, they're active, there are bonds to break, they're ready to kind of participate. So those two things have a great effect on the equilibrium. And again, solids and liquids, usually we leave out. Now, what happens if you need to, for example, go from the Kc value to the Kp value? And you may want to know why would you need to do that? Maybe you're given a problem where all you have are concentrations, but you really need the Kp value. So you could calculate the Kc value and then convert it to a Kp. Or vice versa, if you have pressures, but you really need like the Kc value, you could also calculate. And that is what this equation is here. This is the equation that will allow you to go between the two. So the Kp value is equal to the Kc value times RT delta N. The R and the T is really our ideal gas law stuff. So that is the not the one with energy, 0.08206 version of it, or 0.0821 if you want to use that, that's perfectly fine. T here is temperature, which should be in Kelvin. And delta N is actually the change in the number of moles. And that is basically the moles of the products minus the moles of the reactants. And it's really important when you calculate delta N, and people screw up on this all the time, that you actually do that. You do the products minus the reactants. So for example, if I had, say, this equation here, a reaction, I had, let's say, so if I have this and I wanted to calculate my delta N in this case, my delta N in this case is products, which is 1 gas molecule, minus my reactants, which is 2 and 1 is 3. It is -2, yeah? And that -2 is really important when we look at the equation, because when we just take the RT delta N part, if I do 2 versus -2, there is a mathematical difference, right? 2, you're just squaring. -2 is you're taking 1 over it, right, and squaring it basically. So mathematically is different. So a very common mistake people make is when they do this, they just take the difference and don't worry about the negative or stuff like that. You do need to worry about the negative if it is negative, because that will affect obviously when you pop it into really this part right here. You're going to get a different answer or the wrong answer in that case. So you want to make sure that if that difference is negative and you want to do products minus reactants, that you just don't ignore it, because mathematically you will get the wrong answer. Any questions on that there? All right, so in a homogeneous mixture, as I just mentioned, we really don't include water, or that is a liquid, by the way. So if water is not a liquid or in a liquid state, then you would include it. If it was, say, in steam, which is a gas, right, you would include it. But in the liquid state, we wouldn't include it. So normally what we would do is write the equilibrium expression and take our products divided by our reactants, and we would get something like this. Water, which is a pure liquid, will pretty much stay constant through that process. And that gives us really the equilibrium constant that we should write for this reaction, which is basically the concentration of acetate times the concentration of hydronium ion divided by the concentration of acetic acid. Again, we do not include the water as it is a pure liquid. And as I kind of jumped ahead a little bit, we do not include solids either if you have a solid in there as well. Any questions on that there? All right, so take a moment here, write the Kc and Kp if it's possible for each of these reactions and see what you come up with. Write the expression for it. Okay, so let's take a look. So again, it's products over reactants. So for our first one here, we could write our Kc. Again, should be the concentration of NO2. Once again, we will have to take it to the 4th power there because of the coefficient, times the concentration of O2, which is to the 1st power, as is a 1, divided by our reactants, which is N2O5. Once again, we do need to square it because of the coefficient in that case. In this case, for the first one, we can write a Kp because we got gases going on there. So we could write our Kp in this case would be the partial pressure to the 4th of NO2 times the partial pressure of O2 divided by the partial pressure squared of N2O5. Any questions on that one there? For the bottom one here, we could write our Kc. Our Kc will again be our product, so that is H3O plus times F minus divided by our reactants, which is HF. And should I include the water here? I should not, because again, it is a pure liquid, so that would not get included in this particular case. Can I write a Kp for the guy on the bottom? I cannot. There's no gases, right? So no gases, not so much pressure happening, so you can't really write it for it. To write a Kp, you really do sort of need some type of gas being present in order to kind of do that. Any questions on that there? Now, what happens, for example, if I had something like this? Let's just say, I have something like this. This would then be, the K would be just the concentration of B, as we would not include, obviously, our reactants in this case, so it would just be our products. If I had something, say, like, there we go that way too. We'll go with C, solid. Let's say I have a solid here on the product side. That would not be included, but our reactants would. We would go with 1 over our reactants in this case, yeah. So again, if you happen to have some type of situation like that, where you would not include anything on the product side, you just go 1 over the reactants and put those guys in. Any questions on writing those things? All right, so let's try one with calculation here. The equilibrium concentrations for the reaction of carbon monoxide and molecular chlorine to form CoCl2 are concentration of CO 0.012 molar, concentration of Cl2 0.054 molar, and the concentration of CoCl2 0.14 molar. What is the Kc and Kp value in this case? So give it a go, see what you come up with. So clearly, we have some equilibrium concentrations, and I think I mentioned it, but just to make sure everybody's on the same page, obviously, if you're going to use a Kc or Kp or any equilibrium sort of expression, they do need to be either equilibrium concentrations or pressures to go into there. In this case, so we're looking for both the Kc and the Kp value, and we are given concentrations, so it would make sense to calculate which one first. The Kc, right? Since we do have the concentration, so that seems logical as to where we should start. We'll start with our expression, which is the Kc would be our products in this case, CoCl2 divided by Co and Cl2. Everybody's included because they're all gases. At this point, we could just put in our numbers. So we got 0.14, we got, where is that there? 0.012 and 0.054. And if you put that into your calculator there, you get some type of number, probably with some digits. I mentioned. About a 216, or for sig figging still around this time, about 220-ish there on our significant figure answer, since everybody looks like twos in that calculation. Any questions on that one there? Now that we have the Kc, we could use that formula that we saw that will allow us to go from the Kc to the Kp, where the Kp equals the Kc RT delta N. We do need to do a few things along the way. We do have our temperature here in Celsius. It does need to be converted to Kelvin, so we'll add a 273 to that, and that would get you a 347 Kelvin. We also want to figure out our delta N in this case. And remember that we want to go our moles of products minus our moles of reactants. On the product side, we have one gas molecule. On the reactant side, one gas molecule there, and one more makes two. That's going to give us, again, a -1 here for our delta N. And again, that negative is important. That, I think, is everything that we need. So our Kp in this case, going to be our Kc, so either the 220 or 216, depending on which one you use there, 0.08206 times our 347, and again, that whole thing is to the -1. Again, a reminder that you want to do what's in the parentheses first there. So that's a 347 times 0.08206. And then take it to 1 divided by that answer. So if you clean up what's in here, you got like 28.47482. Then you need to take that to the -1 before you do it. And at that point, you will end up with the page turning. You will end up with 0.0351187. If you do that, then you want to times it by the 220 or whatever number you're going to go with there. And that's going to give us a Kp value of about 7.7 in this particular case. 7.6 if you did 216 number along the way. Question on that calculation there. Small value, large value K here. Large value, we would expect products, right, in this case. Again, as you can see, which is what happens in most cases. Again, the Kp and Kc value are usually not the same numerical value, but they both would be considered a large value as they're both over 1, and they both will basically tell you kind of the same idea there, that you should expect products at equilibrium. Question on that there. All right, we'll lay